Welcome back to what is now the second to last in the Lockdown Math series. So we've been talking a lot about exponential functions and complex numbers and the interplay of the two of them, and I thought what might be a very nice culminating topic to help bring it all together and show really the full breadth of what exponential functions are and what they can be would be to talk about raising I to the power I. Now this is a funny little expression because usually if we think about powers, if we were doing something like I to the fourth, we know how to think about it in terms of repeated multiplication. We're just multiplying something by itself 4 different times. And in general, you'd like to think of I to the x as some variant of that, but as soon as x becomes a complex number, we should realize that it's really nothing like the above. So it's really nothing like this. Instead, the way that we think about it is going to have to be very related to the way that we think about raising e to various different numbers, e being that kind of home base for us. And in fact, if we go, let's not show where things are going too much here. If we go ahead and rewrite that base I in terms of e, it can help us make sense out of this expression. But I don't want to do that. I want you to do that for me. So if you head on over to 3v1b.co/live, link is in the description. It'll forward you on over to item pool, which now asks us, write a value of x so that e to the x is equal to I. That way we'll be able to replace it in the base of our expression. And then once we do that, maybe we can use our knowledge of e and exponentials of e in order to make some sense out of this expression. Now let me just add as a quick reminder, while everyone is rolling in with answers for that when we write e to the x, and complex numbers are in the mix, we are no longer talking about repeated multiplication. And instead, I think the healthiest way to think about it is that e to the x is a shorthand for this polynomial that I might call exp. It's sort of the main exponential function. All other exponential functions derive from this in a way that I'll describe later on in this episode, actually. And it's a lovely polynomial. It's 1 plus x squared over 2 plus x cubed over 6. Each term looks like a power of x divided by the factorial of that power. So the reason for doing that is that it can actually make sense to plug in things like complex values. And one of the things that we looked at earlier in the series was how if you're plugging in imaginary values, let's say I go over here and I'm going to plug in I, where I is the square root of -1, times some value theta, we can very literally read off what it means to exponentiate it in that context. For example, this very first term 1, we might think of as a vector pointing from 0 to 1. The next term, which is some scaled version of I, well, it's a 90-degree rotation of that first vector scaled a little bit differently. Then the next vector is a 90-degree rotation of that scaled differently. And depending on what this value theta equals, the way that these things scale is going to look very different. And it's in general a difficult thing to think about, but it's at least a sensible thing to think about, right? So that when we go to our expression, e to the x, and we're going to start thinking about I and various complex numbers, it makes sense computationally what it means. And then there's going to be a separate illustration that I'll pull up in a moment for how it makes sense in terms of intuition, what it means. But first, let's just see how people are doing on our live quiz, finding a value of x so that e to the x is equal to I. Now, how have people done here? Okay, so the top answer is, in a sense, absolutely correct, you could say. By definition, the natural log is the inverse function of exponentiation. So whatever the answer is here, we should be able to write it as natural log of I. The problem is that's not really helpful. It's not going to move us forward because if we try to use that, we pop over here and we say instead of writing I, I'm going to write e to the natural log of I, and then I'm going to be raising that to some kind of power. It begs the question, and the only thing I can really do from here is simplify that down to be I, which sort of gets us nowhere. So to move forward and to think, is there a number, some concrete point on the plane that I can plug in? For that, we'd want to look at, I accidentally skipped ahead of my questions here. Let me go back, pull up people's answers. Got a little excited, a little trigger happy with some of my clicking around here. And the second most common answer is something that's going to actually help us move forward here, which was 1/2 of I times pi. And then that's the same as what was categorized as the third most common one, 1/2 pi times I, just swapping the two numbers there. And I think the one following that, I'm guessing people either forgot to mention the I, But let's just write that out and kind of see where this moves us. 1/2 I times pi. Now, if you're confused about where that came from, I think this is a good time to remind ourselves of Euler's formula and what it's really saying. It's 1/2 pi times I, where again, computationally, this very literally means if we plug in pi over 2 for theta here, which would be something like 1.57 or so. Let me see if I don't think I'll be able to get it right on the head, but something in the 1.57 range. If you were to play out this whole sum, the claim of saying that e to the pi halves I equals I is that when you play all of this out and you add all of the terms together, you're going to get to the top here. But usually this is kind of a complicated way to think about it. People don't want to pull up this whole polynomial and imagine the spiraling sum. I think it's helpful just in case you find yourself doubting the reality of what we're talking about or the fact that it's something sensible. Almost always, anytime that people are thinking about complex exponentials, instead they find themselves thinking something like e to the I times theta. They just immediately know of, well, maybe not immediately, but you come to immediately know of Euler's formula, that it's telling you, you walk a distance theta around the unit circle, which is to say an angle of theta radians, and whatever point you're sitting at on the complex plane, that's the output. So people who knew about this would say, I, as a number, is also sitting on the unit circle, so I just have to walk an angle of 90 degrees, pi halves radians. And from here, we can actually move forward and get kind of a funny looking answer. Because that I will hop to the inside, and we'll be looking at e to the pi halves times I squared. I squared is -1 by definition, so this looks like e to the negative pi halves. That is a purely real number. You could just plug that into your calculator, and it's actually around 0.2 or so. It's about 1/5, which is weird, that you take an imaginary number and raise it to an imaginary power, and that gets you a real number. Maybe it feels a little bit weird that e and pi have shown up. Not that much if we're thinking in terms of Euler's formula and all of that. But I kind of want to go deeper on this one, right? I think it's one thing to plug in some numbers and see what pops out. And there's a couple great videos who have talked about I to the I from some of my favorite channels. Stand Up Math with Matt Parker, he talked about I to the I, did a beautiful job. Black Pin, Red Pin did another I to the I video, truly great. One thing that I try to do is add something into the mix if I'm talking about a topic that others already have. And in this case, I think one of the most interesting questions you can ask before we jump in, I mean, there's lots of interesting things about this expression I to the I, but if we're seeking intuition, thinking about how I is a 90-degree rotation, right? That's the way that it acts when we're multiplying things on the complex plane. We think of it very intuitively as the thing that, upon multiplication, turns stuff 90 degrees, or pi halves radians. So when you look at this expression that I to the power I equals e to the negative pi halves, it begs the question, in what sense do two 90-degree rotations combine to make this real number? This very specific real number of e to the negative pi halves, around 0.2079, on and on. And it's like those games that sometimes you play with arithmetic where someone says, oh, I'll give you the numbers 1, 3, 4, and 6. See if you can combine them in some way with addition, multiplication, division to get some other specific number, like 24. In that case, is a particularly fun puzzle. In this case, it's kind of like that style of puzzle on steroids. How do we take the idea of a 90-degree rotation and combine it with itself twice in some mathematical sense such that we get out this number, e to the negative pi halves? Where's that intuition coming from? And the first step, I would say, is to remind ourselves of the intuition for why it is that Euler's formula works. Why it is that I can take an expression like e to the pi halves I and say that that's the same thing as I. You know, I just showed what it means in a very computational sense, what the claim is with this spiraling sum, but that tells us nothing about why it would be the case that this is how things behave. Now I've, at this point, made quite a number of videos on variants of this, but I think the quickest one is to think of it dynamically somehow. So if we take an expression like e to the I times t, and we're thinking of that as describing a dynamic, you're going to have a position that changes over time, then what I'll do is I'm going to start drawing that with a blue vector. And we know as an initial condition that when we raise e to the 0, that's at 1. So where we are at time t equals 0 is equal to 1. But let's say that's all we know, right? We haven't been told about Euler's formula or how we should be thinking about it with circles or anything like that. That's just where we're starting. Well, one thing we might know is that e to the x is its own derivative. So if we're thinking of dynamics here, we might ask about the velocity of our position, taking its derivative. And Because e to the x is its own derivative, this is quite nice. The outer expression is going to stay the same. And then the inner expression, as we're applying the chain rule, is just I times t. So we multiply the whole outer thing by I. And this gives us a literal way to read the equation in terms of dynamics, right? What we're saying is take whatever your position vector is. If you rotate that 90 degrees, you apply this action of I, that's going to give you the velocity vector. So wherever you're standing, draw a vector from 0, the origin, up to where you are, rotate that vector 90 degrees, that gives you your velocity. And that's enough to tell you how to move, assuming you know where you're starting. And of course we have to draw this out in the complex plane. The fact that we've rotated 90 degrees already brings us there. And I could draw out a bunch of different potential position vectors, suggestively maybe putting them on a circle, and saying, really, imagine yourself sitting at any one of those and following the rule for this dynamic. And what it would tell you is, okay, I've got to sit there, rotate my vector 90 degrees, that describes my velocity. And it doesn't necessarily have to be any one of the points on that circle. Any point in the plane, if you were following this dynamic, you say rotate that vector 90 degrees, which if we're drawing a vector field, we often scale down. And that's all well and good. And here, you could phrase this question without even talking about exponentials or complex numbers or anything like that. And in fact, I'm going to go back to the quiz just to really emphasize that Euler's formula and what it's claiming, and then how we apply it to expressions like I to the power I, it's really intuitive as soon as we're putting some dynamics into it. And we can ask questions removed from the idea of exponentials that actually have the same substance in their answers. So here, I want you to imagine starting a walk from the point 1, 0 on the coordinate plane in such a way that at all moments, your velocity vector is a 90-degree counterclockwise rotation of the vector drawn from 0, 0, the origin, up to where you are. After pi halves units of time, where will you be on the plane? Okay, so kind of think about that. Think about that dynamic and where you'll end up after a little bit of time. While you answer, let me see if we have any questions that have popped in from the audience. No questions at the moment, at least that I see. So if ever you do want to ask, go to Twitter, use the hashtag lockdownmath. Those will be forwarded to me, and then sometimes they'll be on the screen that I can pull up here. And that always makes for a fun time. For example, it seems like now we actually have one, which is how about other solutions to the expression x equals I, such as 5 pi halves? Oh, I'm so glad you asked. I'm so very glad you asked. We will certainly be talking about that. And if you just hold on for like one little moment, that's exactly what we're going to get to. So I'll keep that on file for us to pull up in a little moment. But right now, while we're just trying to get intuition around the first, there will be multiple answers. The first answer we saw was e to the negative pi halves. Let's consider this lake question. So it seems like most of you correctly said that this would get you at the coordinates 0, 1. It's essentially walking you a quarter of the way around. I said lake question. I'm sort of picturing in my head as a big circular lake that you're going for a walk around, because when you have this rule for dynamics where your position vector rotated by 90 degrees gives you your velocity vector, that is circular motion, because the tangent line to a circle is always perpendicular to its radius. So this rule of motion corresponds with walking around a circle, and that's kind of the intuition for Euler's formula, right? That you keep increasing that value of t, and this dynamical rule, if e to the it is going to behave according to the derivatives that we expect of a function like e to the t, necessarily walks you around a circle. So in particular, when we're wondering how long does it take to get to I, you would basically say just wait for an amount of time equal to, well, whatever the angle to get up there is, pi halves. Okay, so in this case we're thinking pi halves, let me see if I can get it exactly on the dot. Okay, 1.57. We're thinking pi halves as kind of an amount of time for these dynamics to get you on the number I. And that gives us the first half of our intuition if we want to go back to our formula. And we're asking, in what sense do two 90-degree rotations combine to make e to the negative pi halves? Once we're thinking of our dynamics here as each one of your velocity vectors is a 90-degree rotation of your position, this base I, the way that we're kind of thinking about it, reading it off as something with meaning rather than just a number, is that as a point on the plane, it's where you get after traveling for pi halves units of time according to the dynamics of this expression, according to the idea that your velocity is always a 90-degree rotation of your position. Okay, so that's awfully nice. And in fact, there's already sort of two different i's at play here, or I guess there's three different i's at play. We have this base, which is describing the 90 degrees that we walk around the circle. We have the I that's sitting here, which is describing the rule of rotating your velocity vector 90 degrees. But now we're going to introduce another I, which essentially has this effect of changing what your dynamics are. Because as we go from e to the I times t, and instead we raise things to another power of I, which I'll just write with a little caret I. If we take e to the it and we alter what that expression is by raising it to the I, what we get is e to the negative t. Okay, so we have e to the negative t. And if we try to interpret that with the same sort of dynamics that we had above in terms of a velocity and a position, what that's telling us is that the derivative of our new dynamic, e to the negative t, is equal to, well, now the constant sitting in front of t is -1, so our chain rule will have it be -1 times itself, times e to the negative t. So whatever your position is, now your velocity is -1 times itself. So the effect of raising to another power I is kind of like we took the dynamics, we looked at every velocity vector, and we said rotate another 90 degrees. So that in this context, it would actually be, in the beginning, a velocity vector pointing backwards with 1 unit. So if you're starting off at the number 1, your initial velocity is to walk straight towards 0. And as you walk even lower, if you were sitting at 1/2, then you would still be walking towards 0, but now your velocity vector would be -1 times where you are, which is -1/2. And what this means for the actual motion that this would imply, you might kind of imagine it, I haven't animated this nicely yet or anything, but if you look at this whole vector field and you ask each one of those vectors, take wherever you are and rotate another 90 degrees, counterclockwise, they would all be pointed in towards the origin. So if you were to have a little dot move in such a way that its velocity always matches whatever vector it's sitting on top of, what you would end up with is something where with each time step, it kind of takes a step towards 0, and it just, with each of your time steps, is walking towards 0, and each step has a size that gets smaller and smaller as you actually approach 0. And of course, in practice, this would be a bunch of infinitesimal steps rather than very concrete sizing. You might be very exact about it if you wanted and say, what we're looking at is scaling down by some number just less than 1, and we're doing this n different times, and then we're going to multiply that by however much time we're waiting. And you take this as a limiting expression. That's just what we talked about in the compound interest lecture, if you're curious, and it's kind of the standard way to talk about e to powers, is this sort of limit. You could also have that t living on the inside here instead if you wanted. But now, if we think about our original point I, our base, what that meant, it was saying, look at our dynamics, and it's the point you get to when you wait pi-halves units of time. So the effect of raising to the I changes our dynamics in such a way that instead of walking around a circle, we're doing this kind of exponential decay. We're moving towards 0 at a slowing and slowing rate. And the place that you end up after pi-halves units of time will be e to the negative pi-halves, around 0.2079. So, that's a little bit of intuition for in what sense do two 90-degree rotations combine to get you this very specific value. One of them changes your dynamics, and the original one came from the idea of walking pi-halves radians. So I think that's kind of satisfying in its own way, because otherwise when you look at the expression I to the I equals e to the negative pi-halves, it's like, well, what does any of this mean? This doesn't correspond to any, thing that I might see in the real world. But thinking through the intuitions actually have you thinking through things like, what are the dynamics of circular motion? What are the dynamics for exponential decay? Things that come up in the real world all the time. But there is a potentially more pressing question, which was raised, and let's see if it's still up there. Well, whoever asked it a little bit earlier, what about other solutions to e to the x equals I? I think that's actually spot on. And in fact, let me ask other people to contribute some solutions here. So let's go to our quiz. Let me go to question number 3, which is going to be very similar to a question that was already seen, which is to write a value of x other than the one we just saw, x equals pi-halves times I, so that e to the x equals I. And feel free to be as creative as you want to try to get an answer that other people haven't written, right? Just to really emphasize that there are actually quite a few different options here. And then in a moment, we'll talk about why there are quite a few options if it's not already clear. But I'll give you a moment to think of which of the many possible values of x you could choose is the one that you want to put your fingerprint on, that you want to be contributing to the live stats page that we're seeing right now. So I'll give you a little moment. And as you're answering that, we've got a question coming in that says, wouldn't it be more accurate to say that I to the power I is I different 90-degree rotations, not two 90-degree rotations? After all, it's multiplying by I, that's the rotation. So if we stretch the meaning of words too thin, aren't we multiplying by I times? I mean, I think the most honest answer here is just no, not at all. No offense meant, but that's just not what exponentiation actually means as soon as we're extending to the idea of complex numbers. I get the intent. You kind of want to stretch the meaning of taking I to the I. It's as if you're multiplying by itself I different times. But I cannot think of a way that actually like satisfactorily makes sense in my mind. What I do think makes some sense is to try to think of the function I to the x. Say, what properties do we want this function to have? And in the context of counting numbers, you know, if n and k are just things like 3 and 5, we know that it should satisfy this idea of multiplying the outputs correspond to adding the inputs. So we want to say if this is any kind of function, and I've said this in many different forms in many different places, we want it to satisfy the property that when you add the inputs, you multiply the outputs. That to me is kind of what exponentiation is, more so than trying to stretch the idea of repeated multiplication. I mean, correct me if I'm wrong. If you can find some way where, if you read this off in a stretching language context, saying we're taking a 90-degree rotation and applying that I different times, that's not nonsense and that somehow like intuitively gets you to the answer e to the negative pi halves, I'm all ears. But I think the healthier relationship to have is to say we have this central property for exponentiation, which definitely holds in the context of repeated multiplication, but to extend beyond the places where repeated multiplication makes any sense, because it just doesn't make sense when we're talking about something that's not a counting number like I, or other crazy things that we exponentiate in math like matrices. Focus on the property more so than what some people think of as the origins of that property or the original intuition behind it. And an interesting question will be, is there just one such function that feels reasonable to write for this? Because, if we're going to write it as I to the x, not only should it satisfy this, it should also satisfy, when we plug in the number 1, we get I. Presumably I to the power 1, however we're thinking of this function, should be I. Is there just one such function, or are there multiple such functions? That's what the quiz question is starting to get at, and we've got lots of different answers, which always makes me happy. So let's see some of the variety that people have thrown in here. So we've got 5 pi I halves. Great, that absolutely is another value that we could plug in for x here. And just to spell out that a little bit more visually, if we were to look back at our circle here, where we've at the moment walked for an amount of time equal to pi halves, which is 1.57, what if instead we took another full turn and we go another pi halves to get us to pi, which we might kind of record, that's where the e to the pi I value is. We walk another pi halves, we walk another pi halves, which at this point we would have gone a full circle, getting us back to 1. And then we walk for 5 pi halves, which numerically is about 7.85. Yeah, that absolutely is another number that gets us on top of I. And if we were to go through the whole rigmarole of re-expressing I to the power I by first writing e to the 5 pi halves I to the power I, those i's multiply to become negative, and we'd be looking at e to the negative 5 pi halves, which is a very different number, right? We can actually calculate this. I'm not sure off the top of my head, but let's take a look at Desmos maybe. Go over here, let's ask it, what is e to the negative 5 pi halves. 0.000388. Okay, 0.000388. Much smaller number, 0.000388. Which begs the question of, okay, I to the I, what are you, right? Are you about a fifth, like we saw before, around 0.2, or are you this much smaller number? And in terms of our intuition, it's basically a question of how we're interpreting that base I, right? Are we thinking of it as you wait about 1.57 units of time, and then you translate your dynamics into something that looks like decay rather than spinning, and see where you decay to after that amount of time, which is 0.2? Or do you wait even longer for about 7.85 units of time, which is 5 pi halves, and see what happens when you decay for that long, which gets you to a much smaller number? But that's not the only answer that we could enter, right? We have other people coming in here with negative 3 halves times I pi, which, in terms of a unit circle, we could think of as saying, hey, if I want to get to I, rather than walking 90 degrees, pi halves radians that way, what if I walk 270 degrees the other way? 3 pi halves radians, which maybe I'll think of as negative because the convention is usually that counterclockwise is positive. That absolutely is another way to express it. And that would get us a different answer. If we had e to the negative 3 pi halves I, all to the power I, we go through the same game. Now the I squared cancels with the negative that's already there, and we have a positive 3 pi halves. And numerically, this gets us an even different looking answer from what we had before, which if we go over and we say, hey, what is e to the 3 pi, not 3o, 3 pi halves, 111.31. Very different kind of number than what we saw before. 111 point, what was it? 111.31. Great, 111.31 or so. And again, in terms of the intuition, what you might be asking there is, suppose we have this rotating dynamic, but we move backwards in time. We see how long ago in time would I have to be, such that if I played things forward from there, I would land on the number 1, my initial condition. And you have to go back in time 3 pi halves units. And then if you were to translate to the decay dynamics, which is what raising to the I is doing in this context, you say, if I'm starting at the number 1, but I want to move backwards in time and say, where should I have started if I want to decay down such that I end up at the number 1 after 3 pi halves units of time? The answer is evidently starting at around 111 for that kind of exponential decay. And you can see where this is going, where there's actually infinitely many different values that we could plug in for x, if we're thinking of e to the x as being I. And people have entered a lot more here. Excuse me, throwing my pen onto the ground, as one does. Classic for 3rd place. 9 pi halves, great choice. 1729 pi halves, y'all are my favorite. Lots and lots of different options, infinitely many different values, which feels a little disconcerting at first, right? Because we look at an expression that seems like there's just going to be some computation. I just plug that into my calculator and see what pops out. And we've got multiple different values for it. So what's going on here, right? What's going on? And I think this really cuts to the idea of how we think about exponentials in general. Right? But before that, I do want to emphasize that this isn't the only time in math where we come across a kind of ambiguity for how to interpret something. Because if I say something like, what is the square root of 25? I think a lot of us say, well, it's 5. But if we are saying, what should the square root be? It should be some number, x, such that when you square it, you get 25. Well, there's 2 different answers to that. Who's to say that our conventions should be that the square root function is gives us a positive number rather than negative 5? So we have one expression that seems like it wants to have multiple different values, right? And this could actually happen in another context, where instead of square roots, what if I was asking for the 4th root of something like 16? Usually we would think of this as positive number 2, right? 2 is a number such that when you multiply by itself 4 times, you get 16. Seems like a decent answer to a 4th root. But if we're thinking of this as answering the question, what number to the 4th equals 16, there is another answer to this. We could also say negative 2. That's a number that when you multiply by itself 4 times, you get 16. But there's another answer. You could say 2 times I. That seems valid, but there's another answer. You could think negative 2 times I. All 4 of these numbers satisfy that property. So who's to say that the fourth root of 16 should be 2? And the answer ends up being, well, we adopt a convention. When there's multiple options like this, when you have a multi-valued function, we often just choose one of those values to be what we mean when we want to treat it as a function, as something with a single input and a single output. In fancier lingo, this comes up all the time when we're dealing with complex numbers, the idea of something as an operation kind of wanting to have multiple values. You'll sometimes hear the phrase branch, where you choose a branch of the square root function, which is to say you choose a certain convention. In real numbers, it's nice and easy sometimes because you say, just choose the positive one. But there's no notion of which complex numbers are like the positive complex numbers when we want to take square roots. Just to give one example, let's say we wanted to take the square root of I, and we want to know what should that be? Because there's multiple different answers. We think of I, again, as this 90 degree rotation. And if we were thinking of it as a 90 degree rotation, it feels like the square root should be something sitting at a 45 degree angle. Maybe that's the square root of I, which we could write out very explicitly as root 2 over 2, root 2 over 2 I. That's just using trigonometry. But if we were thinking of I instead as being a negative 270 degree rotation, it feels like half of that, doing half of that operation, should actually get us on the other side. Maybe the number sitting down here should be the square root of I. And that's actually just the negative of what we saw before. Negative root 2 over 2 minus root 2 over 2 times I. Now, in the context of real valued functions, we can say, yeah, just choose the square root to be whatever the positive answer is. But which of these do you consider the positive answer? Maybe it feels like we should consider this upper one because its coordinates have positive numbers. But however you try to define positive in a nice way here, that's going to be consistent, for example, 2 positive numbers should always multiply to make a positive number, you're not really going to be able to do it the way that you can for real numbers. And in fact, this phenomenon here where we're taking roots is actually the same as the phenomenon we were just looking at when we were talking about multiple values for I raised to the power of I. Because forget I raised to the power of I. Let me ask what might look like a much simpler question of taking 2 to the power 1/2. Okay? What's 2 to the 1/2? I think you say, well, we know what this is. We kind of define it to be the square root of 2. All's well and good. But what if I said, let's approach this the same way that we were approaching our I to the I expression? I want to first express things as e to the something, right? And then I'm going to raise that to the 1/2 by multiplying the 1/2 into the exponent. And I'd say, well, okay, I guess I can do that. E to the what is equal to 2? Well, that's the natural log of 2. It's a constant, which is around 0.69 or so. If we raise e to that power, we'll get 2. So we could be thinking of this as e to the natural log of 2 times 1/2. And if you wanted to, if you were thinking of e to the x, this might be kind of overkill in the context of real numbers, but if you were thinking of e to the x as shorthand for this exp function, you could plug in the value 0.69 times 1/2, which I guess would be around 0.345-ish, something like that. You plug in that very concrete value into your polynomial, see what it outputs, and it will output around 1.414, a nice real number, square root of 2, what you would expect. But if we do the same thing we were just doing with I and acknowledging that there's actually multiple different answers when we want to write something as e to a power, we could also write this might seem funny, but we could write it as e to the natural log of 2 plus 2 pi I. That whole thing raised to the 1/2, right? After all, this value will come to equal 2. You could break it down as it's e to the natural log of 2 multiplied by e to the 2 pi I. This one just has the effect of rotating things 360 degrees, so it's just going to equal 1, so we're looking at 2 times 1. Great, that feels like a valid substitution. And yet when we play the same game of taking this and raising it to a power and treating that by multiplying the power into the exponent, look at what happens. We have e to the natural log of 2 times 1/2 plus, well, what's 2 pi I times 1/2? Well, that will be pi times I. Now this first part, e to the natural log of 2 times 1/2, that will end up being the familiar square root of 2. That's all well and good. But we're going to be multiplying that by e to the pi I, right? And quite famously, e to the pi I is -1. So in this case, it seems to be suggesting that if we are solving this expression 2 to the 1/2 by playing around with the different answers we could plug in for something like e to the x equaling 1/2, what we end up with is another answer, what we might traditionally write as this negative square root of 2. And here, I mean, it's a little funny for it to have multiple values, to look at 2 to the 1/2 and say that's not equaling one thing, but based on choices we make, it could equal multiple different things. But the two things that it could seem quite reasonable. If there's going to be anything that 2 to the 1/2 is, it seems like it should either be the positive square root that we're familiar with, or the negative variant of that. That doesn't actually seem like such a problem. And in fact, we could play this game even further, where let me ask you for even more creative answers to this expression, because maybe we can find other funny powers of something like 2 to the power x as we start plugging in various different values of x based on what substitution we make, if we're abiding by the same rules that we were using in evaluating I to the power I. So this time the question asks, or it specifies that one solution of the equation e to the x equals 2 is the real number natural log of 2. Okay, that one, we know it. It's not boring, but it's boring in comparison to what else we could do. Can you think of another one? Right? Can you write some other answer to the question e to the x equals 2? And again, creativity is welcomed, so I will give you another little moment for that. All right, I will go ahead and lock in some answers here, if that's all right with you. I'm not sure how much time it necessarily takes to do the math entry, depending on what device you're looking at, but don't be too stressed if it's before you got the chance to enter the question that you want, into the answer that you wanted to answer. So it looks like 131 of you have entered the variant where we take ln of 2 and we add 2 by I. And I guess I, in writing this question, mistakenly marked one of the answers as being correct, when in fact there's quite a few different correct ones. So that's on me for the fact that I don't know if it looks to any of you like, oh, it's red, you got it wrong when you entered ln of 2 plus 42 I pi, which is of course a great choice. But you could also have something like 4 pi I plus the natural log of 2, or 6 pi I, or really any integer multiple of 2 pi I. If you add that, it doesn't affect e to the x, because it just has the effect of multiplying by e to the 2 pi I, which is the effect of multiplying by 1. And again, this has kind of a funny consequence where it seems to output kind of reasonable results when we do it. As another example, it looks like the second most common entered expression there was that we might replace 2. So let's think we're thinking of 2 to the power 1/4, okay? There was a suggestion that we replace 2 with e to the natural log of 2 plus 4 pi I, okay? Plus 4 pi I, and we raise all of that to the 1/4, right? Well, if you were to play the same game, you would get e to the natural log of 2 times 1/4, and we'd be multiplying by e to the pi I. Now the first part of that is going to be the usual positive fourth root of 2, the thing we mean when you plug in an expression like fourth root of 2 into a calculator, a nice small positive number. But then this second part is -1. So it seems to be saying, if we were to interpret 2 in this different way, raising it to the 1/4, it's not the usual answer that we'd get, but it's a reasonable answer. It's another number that when you raise it to the 4th power, you get 2. And if we had done this with even different values, if instead we had been using 2 pi I, it's kind of fun to think about how that would have changed things. If instead of 4 pi I, we had been adding 2 pi I, well then over here we would have been looking at pi halves times I, and instead of multiplying by -1, we would have instead been multiplying by I, which again is a valid answer. It seems like a reasonable output for something like 2 to the 1/4. So when you're looking at the fact that I to the power I seems to have multiple different values for it, right? We had this funny phenomenon where we could plug in e to the 5 pi halves I, -3 pi halves I, and we get what seem like wildly different answers. Something super small, something super big, all very different from the 1/5, approximately 1/5 answer that we found before up here. It's exactly the same phenomenon as when you're asking something like what's 2 to the 1/4 and acknowledging that there's actually multiple different solutions to the expression x to the 4th equals 2. 4 different solutions, in fact. And what you're looking at is the fact that there's multiple different solutions to the expression e to the x equals some kind of base, whether that base is I, whether that base is 2, whatever it might be. And one way that we might think about this is that when you're dealing with real numbers, things are just lovely. Things are nice, there's one-to-one relationships, you've got positives, it's great. Where if we want to think about exponential functions, let me just cover some of this stuff up. We have this nice back and forth, where you can choose to express any exponential as a base to x, like 2 to the x, or you could express that same exponential as exp of r times x, which, that is the polynomial that we refer to implicitly refer to whenever we write something like e to the x. And there's a lovely back and forth because you can just take a natural logarithm of b and it gives you one answer, assuming that b is a positive number. And that's the same thing as saying that exp of r is equal to b. So one way that I've talked about this earlier in the series is that if you were looking at the family of all possible exponentials, right, we could write them as exp of r times x and change what r is. And this is exactly the same thing as writing e to the r times x, if that's something you're more comfortable with. So e to the r times x, exp of r times x, those are the same thing. We could think about changing what that is. But on the other hand, if you were to think about all possible exponentials as some base, let me do base to the power of x, and we're going to change what that base is. At first it feels like that's a different kind of expression to manipulate, but it's just another way of expressing the same family. Right? And a way that you might think about this, for how do we think about what base does it correspond to if we're thinking a little bit more abstractly as exp of r times x. And there's a reason I'm doing this, because we're about to apply this to complex numbers where it's going to look weirder. So follow through with me here. If instead of looking at that base, one thing I could do is say, what is the value of exp of r, right? Which is basically this function, but when we plug in 1, so exp of r times 1, if you prefer to think of it that way. And that is being represented by our green line. And what you can see is, okay, if I get r, that factor in front of x in my exponential function, exp of r, x, to be 0.69, which I know is around the natural log of 2, what this means is that exp of 1 is about 2. And so this corresponds with the function that we would usually write as 2 to the power x. Right? Okay. And basically, as I change around my r, I could try to change it to something so that it looks like 3. So around 1.1, that exponential looks like 3, which we would usually write as 3 to the power x. I would like to argue that it's a little bit healthier to think about varying this value r rather than varying the base. And the main reason is that as soon as we get to complex contexts, and we're thinking of exponentiation, you have this overloading that goes on, where if we change around what sits in front of the x, that's all well and good. I could have exp of r times x, where maybe r is something like 0.69, but I could shift that down by 2 pi I, and that doesn't change the base that it would correspond to. That would still correspond to 2. Or I could shift it up by 2 pi I. That doesn't change the base that it corresponds to. Because in all of those cases, when we plug in x equals 1, we get the same thing. However, all of these, for different values of x, are distinct functions. This is why we saw multiple different values for I to the power I. Because I to the x is an ambiguous function in that context. It would be unambiguous if we decided which value of r, such that what we're representing is exp of r times x, which value of r do we choose? As soon as we choose one, it's an unambiguous function. But at that point, it just feels like maybe what we want is to stop thinking about things in terms of some base raised to the power x. Maybe as soon as we're in the context of complex numbers, we should just write them all as exp of some constant times x. If for no other reason, it makes crystal clear how we actually plug in numbers if we want to do a computation or just to do math on top of it. We've got this nice infinite polynomial that we plug them into. And I'll make another case for you that this is maybe the correct way to think about exponentials as soon as we're extending into other domains, things like complex numbers. And for that, let's just back up, go back to, ooh, doorbell, something's arrived. Go back to the original way that we extend the idea of exponentiation and just think of like, what is 2 to the x? Right? we know how to think about this for natural numbers, something like 2 to the 3, repeated multiplication. How is it that you're first taught to think about something like 2 to the x for fractional amounts or for negative amounts and things like that? Well, you're usually taught that 2 to the 1/2 should be something where, if I multiply it by itself, and this follows the usual rules that exponentials do with counting numbers, where we're able to add things in that exponent, I should get 2 to the 1. So it should be some number that when I multiply it by itself, I get 2. And at that point you have a choice. Maybe it's positive, maybe it's negative. But if you always decide to make the positive choice, you're going to be able to get a nice continuous function out of this. Same deal if we ask about negative numbers. What should 2 to the negative 1 be? Well, that should be something where when I multiply it by 2 to the 1, it gets me 2 to the 0. And that's kind of the justification for our convention that negative exponents look like 1/2. But what's really going on here is we're saying, whatever this is, it should be some kind of function that satisfies this property. F of a plus b equals f of a times f of b. And moreover, the fact that the base is 2 is basically telling us that it's not just any such function. It's a function where when we plug in 1, we get 2. And just as a little, sanity check style question to see if you're following along with some of the implications here, I want to ask you, what is, I won't call it like a softball, but this isn't meant to be like an incredibly deep question necessarily. It's just more of a check if you're following along with the idea of abstractly starting with properties of a function and then kind of deducing ways that we might want to write it down based on those properties. If f of x satisfies this exponential property, f of a plus b equals f of a times f of b for all inputs, and it also satisfies f of 1 equals 2, which of the following is true? Which is to say, which of the following is necessarily true, no matter which such function you're starting with. And those of you who remember, which lecture was it? It's whichever one we were talking about how to what Euler's formula is really saying. I asked a question of this style where I neglected a single condition. I didn't write down the fact that we want to make sure f of x is non-zero everywhere. And then that caused some amount of confuddlement, which is cool. Get confuddlement on screen. That happens to all of us. But the intent of it was to basically show that this abstract property of something that turns addition into multiplication is enough to basically make you want to write the function as whatever it equals as 1 raised to some kind of power. This is the spirit of the question. Now, we've got a couple questions actually about power towers that seem to have popped up here, which is great, connected to last time. Let's hold off on the power tower question for just a moment so that we first get like a deeper feel of like what exponentiation should mean here. Because we can what I want to claim is we can answer it in like multiple different ways. So if you give me just a moment, we'll talk about power towers. And then just as a number line can be represented in a logarithmic scale, can the same be done for a complex plane? Maybe mapping the complex plane onto an infinite cylinder in the logarithmic sense. Yeah. In fact, there's a visualization that I'm going to get to in just a moment here where we do something quite similar to that. Because what we'll do is play around with different exponential functions, x of r times x, but we're going to change that value of r, which is going to be represented by a little yellow dot. So we'll kind of talk through this. It's not going to map the whole plane, but just a couple sample points from the real axis and the imaginary axis. But the idea is that as we move around what that constant is, we're going to be able to kind of visualize the different things that it does to the plane. And effectively, it's like it's turning the x-axis into a logarithmic scale and then wrapping the imaginary axis along a circle. And then as soon as that value of r becomes imaginary, it swaps the role of those. Real numbers get put on the circle and imaginary numbers get put on a logarithmic scaled positive axis. So great question. All three of which I guess are sort of jumping the gun ahead for where I want to go, but nice to see that's where people are thinking. So on this one, let's go ahead and just grade it. The idea is that this property of f of a plus b ends up letting you express a lot of different things purely in terms of what f of 1 is. And just to spell that out very explicitly, something like f of 5 is the same thing as f of 1 plus 1 plus 1 plus 1 plus 1, which is the same thing as f of 1 multiplied by itself 5 times because of this property. which if f of 1 is 2 is the same as 2 to the power 5. And then something like f of negative 5, it should be the case that when we multiply it by f of 5, we get whatever f of 0 is. And it's not immediately clear what f of 0 is, but we could say that f of 1 plus 0 is equal to whatever f of 1 is times what f of 0 is. But f of 1 is equal to 2, and so this is also equal to 2. So we're saying 2 is equal to 2 times something. Well, that something has to be a 1. So in this context, this guarantees that f of negative 5 is 2 to the negative 5. It's 1 over 2 to the 5th. So we could explicitly write this as 2 to the negative 5. Which is all to say, these two properties together make us really want to write the function as 2 to the x, because any counting number that we put in, it's going to satisfy, it's going to look like 2 multiplied by itself that number of times. Any fractional number we put in, it's going to satisfy these properties that we wanted. And you might wonder, is that unique? And in the context of real valued functions, it actually would be. But in the context of complex valued functions, there would be multiple such functions f that we could write for this, one of which is what we were looking at before, where we could have a function defined to be exp of the natural log of 2 plus 2 pi I, all of that times x. Okay, forgive the sloppiness here. I just get excited writing about this. And this is actually a different function, as evidenced by what happens if you plug in x equals 1/2. Right, we saw a little bit earlier how when you plug in 1/2, what you get is the negative square root of 2. And then if you plug in 1/4, you get not the 4th root of 2, but I times the 4th root of 2. So it is a different function, but it still satisfies these properties, and it kind of makes us want to write it as 2 to the x. And it makes it suggest that maybe 2 to the x is an ambiguous bit of notation, and we should just write everything in terms of exp of r times something. But you might wonder, well, maybe we're just not being creative enough with all of the functions that satisfy this property. Maybe there's an ambiguity when we write exp of r times something, and there's different values of r that could come into play. But I'm just going to put down a little claim, and then maybe give like a sketch of what the proof would look like if you want, which is that, let's say you have some complex function f, and it satisfies the following properties. First, you're able to take a derivative of it. It's differentiable, which just keeps it from being some, totally messy, discontinuous thing that's like taking on some random values depending on, the span of whatever vector space over, fractional amounts you might want to think of in crazy ways. It's a nice function that's differentiable. It's not equal to 0 everywhere. So the condition that sort of slipped my mind, and I forget which lecture 4 or something like that. And then it has this central property that it turns addition into multiplication. If you have such a function, I claim that there is a unique, maybe I should really specify, there exists a unique complex number r, so that you could write f of x as basically being this exponential function of r times that value x, which is, basically saying that if you have exp as a function, this infinite polynomial with nice derivative properties and all of that, if you have this, you have every exponential that you want, in a very abstract, generic sense of the word exponential, just based on a property that we could want from it. And the sketch of the proof would look something like this. If you want to first look at what is the derivative of this value, which we're assuming exists everywhere, right? And you explicitly write out what the limit of that is. I'll just talk through it very quickly here. For those who want to pause and think through the details, feel free to. The central property that we have lets us expand out the f of x plus h term. So we're thinking, a slight change to the output over the change to the input that caused it. That's what df dx unwraps to. And because we can factor that out, we can factor f of x out of the expression entirely, and the whole limit is expressed only in terms of h, which, if you think about what it means in the context of derivatives, and the fact that f of 0 necessarily equals 1, this whole limiting expression is just some constant, but more specifically, it's whatever the derivative of our function at 0 is. So you have this funny thing where if you know its derivative at 0, that determines what its derivative is everywhere. And in the context of exponential functions, this is hopefully quite familiar, because all that we're really saying is the derivative of an exponential function is proportional to itself, and that proportionality constant is equal to whatever the derivative at 0 is. This is all very abstractly phrased and such, but the purpose of it is to emphasize that it's not necessarily just functions that we already think of as a to the power x, but it is a potentially much more broad class of functions that just satisfy this abstract property of turning addition into multiplication. But if you have that, it actually guarantees that you also have a second derivative, and for that matter, a third derivative and such, because the derivative function is just proportional to itself. So in order to take the nth derivative, you just look at that proportionality constant and raise it to the power n. And then from here, you could do a Taylor series expansion, and I might leave that as sort of the advanced homework for those of you who are comfortable with Taylor series and that idea, especially if you want to intermix the idea of any differentiable function that's differentiable in a sense of complex numbers, which is sort of definitely a college topic. You could intermix the reasoning there as you want, but fuzzy reasoning is allowed in the context of someone who only knows about Taylor series and nothing else, to take this idea and look at the Taylor expansion for f and kind of justify the idea that there's a unique complex number such that our function f can necessarily be written like this, right? And then the connection to normal exponentials is whenever you have such a value r, we do essentially what we do in the complex context of real numbers, is if you look at exp of that function, of that value r, and write that as a base, it feels like you should be able to write that as b to the x. But the whole point here, of course, is that when we play this game and you're trying to interpret something like I to the x, that's an ambiguous function because there's lots of different values of r. We could interpret that to mean not just exp of pi halves I times x, but we could also interpret it to mean exp of 5 pi halves I times x. And these are separate functions, and there's an infinite family of separate functions that feel like we should write them as I to the x. So the expression I to the I, unless you've adopted a standard for what that's necessarily going to mean, when you say it has infinitely many outputs, another way to think of that is that the function I to the x with the notation we have is a little bit ambiguous. Now with all of that, let's just start visualizing some of this because I think that's fun. And you tell me if this is a helpful visual or a more confusing visual. But what we're going to do is look at this function, exp of r times x, which is basically this is another way to write e to the power of x. In fact, I think I rendered a different animation at some point that specified that because I was planning on doing that. So let me, oh yeah, there you are. Get back in my file system. Get back to where you're supposed to be. Get on in there. Is it complaining because there's multiple different? It's going to be like there's a, oh, replace. It shows up on the other screen. Wait, why is it? Yeah, okay, replace. Replace whatever you see there. And now we go back to, oh, there we go. All of that just so that I could have nicely written out, if you're uncomfortable with thinking of it as exp of r times x, this infinite polynomial, just in the back of your head, e to the r times x. And we're going to vary around r. So I'm going to follow the points of the imaginary axis, and I'm going to follow the points of the real axis. And let's see what this does. Well, that's all kind of fast, so let me think through it a little bit more slowly. All of the negative numbers, anything that's a negative real number, is going to get squished into the range between 0 and 1, which should make sense. E to a negative real number is something between 0 and 1. And we're specifically tracking f of -1, which is going to show up around whatever 1 over e is, around 0.37. F of 1 lands on e, as expected. That's what exp of 1 is. F of I is going to land 1 radian around the unit circle. And it's kind of fun to follow along the whole imaginary axis here, how the imaginary axis gets wrapped around a circle. And what happens as we tweak this value of r, that's determining not just that we're talking about an exponential function, but which exponential function. There's a nice one-to-one correspondence between all the exponential functions we might want and values of r here. It stretches things differently. So when we put it up to 2, it stretches out the real axis a lot more so that f of 1 ends up around where e squared is, a little above 7. F of -1 is much closer to 0. F of I is a 2 radian rotation around the circle. F of -I is a -2 radian rotation. And of course, we can get to our favorite formula that if that were pi that we had as our scaling constant, then the real axis gets stretched out quite a lot. F of 1 is sitting off at e to the pi, which is very close to 20 plus pi, which is always fun, and f of negative 1 extremely close to 0. So it's really stretched out that real axis. And it's also stretched out things in the unit circle direction so that getting to f of I or f of negative I walks halfway around the circle. So that's all well and good. Now, how would we think about a function like 2 to the x, which is what we would also write as exp of the natural log of 2 times x. So we kind of move our yellow dot representing the value of r to around 0.69, still no imaginary part, just a real number, 0.69 or so. That's the natural log of 2. Well, you can see that f of 1 lands on 2, which is why we want to call this function 2 to the x. F of f of negative 1 lands right on 1/2. F of I, it's some walk around the unit circle. Very specifically, it's going to be 0.69 radians around the unit circle. And now we could have a little bit more fun and say, what would happen if we were to change this to, instead of being 0.69, instead of being the natural log of 2, make it I times the natural log of 2, so that we're really thinking of something that might have an exponential base to it. This would be what we might think of as 2 times I raised to a power. Well, if we move that yellow dot, which is representing r, off of the real axis and onto the imaginary axis, it swaps the roles of the teal dots and all of the maroon dots in this context, which, remember, came from being the positive and imaginary axes. And it should make sense that it swaps their roles, because what does it mean if we take the input space and we multiply it by I? It means we're rotating that input space. So everything that was the real number axis turns into the imaginary axis. And everything that was the imaginary axis is getting turned into the real axis. So for us, what that means is our new exponential function, where our value of r is now purely imaginary, takes all of the real numbers and it just wraps them around a circle. And it takes all the imaginary numbers and it's putting them onto the real number line. So in particular, let's say we scale this thing up so that we're sitting at around pi halves times I. Well, what does that actually mean? That means it takes the real number 1 to the value I, which is the sense in which we want to write this function as I to the power x. Right? It just tempts us to write it not as this abstract looking thing, exp of r times x, where r is equal to pi halves I. No, we just want to write it as I to the x, even if that's a little ambiguous. What that really means is just that the function we're dealing with outputs I at 1. And if it's an exponential function that, and we're asking what does it do to the value I, what is I to the power I? In this case, it shoves it to around 0.2, around a fifth. But there's many different exponential functions that would have this property of putting f of 1 onto the number I. So if we were to scale it up even further, I don't think I have it animated here, but if we were to take that yellow dot and raise it up until it got to 5 halves times pi I, what you would see is that the unit circle is rotated around on itself, so that f of 1 would rotate around another 2 pi radians and land where it is. But it would stretch out the real axis a lot more, which was the sense in which another output of I to the I is a much, much smaller number. It was around, 0.0003 or so. But we can also see what I think is quite fun, what happens if we consider alternate expressions that we want to interpret as 2 to the power x, right? So when r is a purely real number, the natural log of 2, kind of makes sense that when you plug it in here, the expression we get is what we want to write as 2 to the power x. But what if we start moving it in the imaginary direction, okay? And what I'll first do is I'll move it up by pi I units. Now, what's going on here? We have exp of r times x, and r is equal to this value, which is the natural log of 2 plus pi times I. What that means is that when we plug in 1, f of 1 is at negative 2, so we want to write this function as negative 2 to the power x, right? And that's actually something that, it's a little deceptively simple when we write a negative number to a power. Negative 2 to the power x. It doesn't at first look like this necessarily brings us into the complex numbers in any way. But of course, when we plug in even a value like 1/2, where we're kind of asking for a square root of negative 2, we realize that we want to write this as something like I times the square root of 2. But if you were to look at this function negative 2 to the power x in the full complex domain that it's dealing with, what you're looking at is a function that takes the value of 1 to negative 2, and if it does that, what it does to the rest of the real number line is it kind of spirals it outward. So we see that f of -1 sits at -1/2, about where you would expect. If you were to follow to f of 1/2, it would sit exactly on the imaginary line, and f of 1/2 would be square root of 2. Oh, my mouse is not where I want it to be. It would be around square root of 2 times I. And as you continue further on, this is showing you all of the real valued powers of -2 to the x. It necessarily spirals around. But we could also move our value of r even higher and get it up to around tau times I, around 6.28 times I. And in that context, this is another function that we would want to write as something like 2 to the x. Because for any whole number that you plug in for x, it will look like repeated multiplication. And it even has kind of reasonable values for things like 1/2, where it spits out the negative square root instead of the positive square root. But what it's actually doing as a transformation to the plane, where it puts everything, is the real number line ends up being a very tightly wound spiral that goes around. And it just spirals in such a way that f of 1 lands right on the number 2. So it is in that sense that we could say 2 to the x is plausibly interpreted as a separate exponential function from the one that we are traditionally used to. So I think with all of that, I will leave things for today. And I'll just leave you with a couple lingering questions to think about. Okay? So if you want to think of I to the I as being a multi-valued expression, right? You could say we adopt a convention. Fancifully, you'd say you choose a branch of the natural logarithm function, and maybe that locks you into this being e to the negative pi halves. But if you say this kind of wants to be infinitely many different values, like the various ones that we saw, how many values does 2 to the 1/3 want to be in the same sense, where we are replacing 2 with various different options for e to the x, such that e to the x equals 2? How many different values does that want to be? Or how many values does 2 to the 3/10 want to be? Phrased differently, of all of the exponential functions, f of x which satisfy, oh, have I written it down somewhere? F of x that satisfies all of these properties that I've written. So if it satisfies all of these, and if f of 1 is equal to 2, right, how many different outputs are we going to get when we plug in x equals 3/10 for the various options for what function that is? And how many outputs are we going to get for 2 to the pi for the various functions that 2 to the x could represent, if we're thinking of 2 to the x as some kind of exponential function, exponential in the sense of these sort of abstract properties, and if we if we have a class of different such functions and we want to plug in pi. It makes me laugh just because it's such a, I don't know, kind of a funny answer that pops out as you're trying to think about it. So those are the questions that I'll leave you with. And I think this is, you know, my central question in approaching today's lecture was whether I wanted it to be kind of describing like these abstract properties of exponential functions. And it's just cool to me that starting from those abstract properties, you get locked into the idea of e to the rx, or more, you know, I think more honestly written x of r times x for different values of r. That it locks you in that far, but it doesn't lock you in as far as having an unambiguous notion of what 2 to the power x should be, much less something like I to the power x. The risk in that, of course, is that sometimes people don't love abstraction, and sometimes it doesn't come off as approachable. But if that's the case, you know, you just let me know. I think there's a whole interesting circle of thoughts that surrounds all of this stuff, to include power towers, because if you want to actually talk about power towers like we were last time in the context of complex numbers, or even with negative bases, you have to be thinking through things like this. So it was a question that we had up on screen. What happens if we do this for I to the power I tetration? You know, let's just try this. Let's just go ahead and try a power tower where we're raising I to a given power and see what pops out of it. So I wasn't planning on doing this, but we can always pull up Python and essentially do what we were doing last time. So the way that this would work is we were starting off with some base value, and then for some kind of range, what were we doing? We were taking a and we were going to reassign it to be whatever the base, which in this case is I, raised to the power of a should be. Okay, cool. So we're going to do that, and then we're going to print off the value of a. And let's just do this for, some much bigger number, like 200. So it seems like what happens is there's potential for chaos with these things. Like sometimes it's not that you've landed on a stable value, or it's not even that you've diverged. It could be that you're bouncing between a cycle of values, or that you're like literally bouncing in a way that's it's not periodic or anything, and it's actually chaotic. I suspect that doesn't happen for I, but it's a thing to potentially look out for. It looks like it does kind of stabilize. Maybe there's some little subjection to numerical error, but we stay pretty consistently around something with a real part of 0.43 and 0.36. Now what I would want to emphasize though is this expression, so let's set a back to be equal to 1. This expression of taking I to the power of a, remember, that's a little bit ambiguous. It depends on what choice of the function I we actually have. So let me import numpy, so I have the exponential function. Let me go for our big range like we had before. Rather than writing it as something that's like I to the power of x, I'm going to write it as the exponential function of a different constant, right? A different constant that I'm going to make, I want it to be 5 pi halves. So I'll do 5 pi halves times I. So it's a complex number, and it's got 5 pi halves as the imaginary part. So this is 5 pi halves times I. And what am I doing? I'm exponentiating that. So I want to multiply a onto the inside there. Okay, this is basically another way that you could interpret the expression I to the x. Fancifully, you would say you've chosen a different branch of the natural log function. But it is another function which we could iterate on itself and see what happens, and we might get a different result. Ah, very interesting. Okay, so we actually have a different result. It looks like what ends up happening is it bounces between two values. Oh wow, is it period 3? That's interesting. Period 3 implies chaos. So we've got 7.35, then 0, then 0.99. So it looks like it gets into the cycle of bouncing between 3 separate values, even though in theory, in both of those cases, we were doing something that was I to the x iterated on itself. It has everything to do with what actual function you think I to the x is referring to. So in that sense, the power tower question is ambiguous. Usually you just choose it to be the pi halves I variant, but it's more fun to see that it can be multiple things. All right, we have addition, multiplication, exponentiation, tetration. Can we think of something in between? Halfway between multiplication and exponentiation. Oh, that's an... I mean, I love the spirit of it because each one of them, it comes down to like a discrete step of you're repeating the previous operation. But oftentimes in math, when you have something initially defined in terms of repetition, like exponentiation, you can extend it beyond that. I can't think of anything off the top of my head, but that's an interesting question. I don't know if that's an extended notion. I mean, you have things like fractional derivatives, you have things like fractional and complex exponents, so it doesn't seem outlandish, but I'm not familiar with one myself. And then lastly, do complex numbers to the power of complex number values arise in physics? And if yes, how does one decide which values are valid? So I can't think of if they necessarily, scene switching. I can't think of if they come up in physics in like a direct sense. And this is probably just because I'm not a physicist, so I would say like ask your neighborhood physicist and see what they have to say. I mean, clearly the point of teaching the lesson here is that the thoughts that you have to go through to make sense out of it do build a stronger relationship with exponentials. Things like, it's not just more natural to represent them as e to the rx. Once you get to complex numbers, you kind of have to represent them that way. Whereas previously in like physics or other real world contexts, it's something that's just nice.